Aice Physics Motion Test, Part 2, Graphing. Question 1. Figure 2.1 shows a speed time graph for a ship starting to move. Describe the motion of the ship during each section of the graph. Section A, the speed of the ship is changing, which means that it's accelerating. And because there is a line here, indicates there is a constant acceleration. So if I want to calculate the acceleration for section A, you need to be careful here because the time is given minutes. So in this case, you'll be the change in velocity, which is from 2 minus 0 over the time is 3 minutes. So 1 minute is 60 seconds. On section A, the ship is moving with a constant acceleration. To calculate this acceleration is 2 over the time here is 180 seconds, 3 times 60 seconds. So that's the acceleration on this section A. On this section B, which is the orange shaded here, the ship is moving with a constant speed, right here, 2 meters per second. Acceleration is 0 because it's showing a horizontal line. At C, the speed is increasing, so it indicates there is an acceleration, and because it's a straight line, so the acceleration is also constant. The change in velocity here for C is 10. Well, it starts at 2 meters per second and ends at 10 meters per second with one interval of 6.5 minus 5, 1.5 minutes. So let's see, the ship is moving with a constant acceleration, and the acceleration here is higher than the first one. This is 0.089, and we can notice because the slope is steeper than the section A. So I added here higher than section A because the line is steeper. At section D, again, the speed is constant and is equal to 10 meters per second. That goes from 6.5 seconds up to, minutes up to 10 minutes. So in this first question, you are required just to describe the motion of the ship throughout this time. Calculation of the acceleration is not required, but if you want to compare, for example, compare those two slopes, that's a good idea to have this value available to you so you can actually compare numerically. Now the second question for the first one, question B. Determine the distance traveled by the ship in section C of the graph. Question 1B. Determine the distance traveled by the ship in section C of the graph. So the section C is shown by this shaded blue area. So this is a trapezoid. So we need to calculate the area of this trapezoid to determine the distance. So if you turn the picture this way, we need to determine a couple things. The big base, which is the longest line here that go up to 10. So that's the big base. The smaller base goes up to 2. And the height is the difference between 6.5 to 5. So here are the dimensions of this trapezoid. So to find the area of a trapezoid is big base plus small base times height divided by 2. The big base here is 10. The small base is 2. So 10 plus 2 times the height, which is 6.5 minus 5, is 1.5 divided by 2. So 12 times 1.5 equal divided by 2, 9. Now, remember this is 1.5 here is in minutes, so we need to convert to seconds. So we have to multiply by 60 right here. So it's 1.5 in minutes times 60 to convert to seconds. So then we can give our answer in meter. Okay, so here is showing how the units work in order to have meter as a result. So 10 meters per second plus 2 meters per second is 12 meters per second. This value here is in seconds, so 1.5 times 60 is 90 seconds. So now I cancel seconds with seconds, and I have 12 meter times 90 over 2. So the results of this is 540 meter. That's the distance. Question 2. A person on roller skates makes a journey. The figure 1.1, which is this one, shows the speed time graph of this journey. A. The graph shows 3 types of motion. Complete the table to show when each type of motion occurs. Use the letters shown on figure 1.1. Add a letter to each of the blank spaces. The first row is done for you. So what happened to when the acceleration is happening? It starts and ends. So acceleration here is happening from W and ends at X. What about deceleration? So deceleration is when the speed decrease the value. So here is showing the decrease of the value as the time goes by. So deceleration starts at Y and ends at Z. And constant speed is right here. It starts at X and ends at Y. Option B, calculate the distance traveled between 60 and 100 seconds. So now we don't have to convert from minutes to seconds, already in seconds, great. So we just need to identify this. 60 to 100 is right here. So 60 to 100 is this pink outline triangle. So it's asking to find the distance. So when you have a speed time graph, the area under the line can give us the speed or displacement. So in this case, the distance, which is the same thing I already mentioned on part 1 of the test. What is the difference graphically to determine distance and displacement? So distance, we add everything, and displacement, you have to watch for the signs for each area. Okay, in this case here, we have the area is the right triangle, base times height divided by 2. In this case, the base is 100 minus 60, which is 40. The height here is 20 divided by 2. So here we have 400 meter. So that's the answer, 400 meters. C, the size of the acceleration is greater than deceleration. Calculate the acceleration and deceleration. So the blue outline triangle here shows the acceleration, and here the deceleration. So let's calculate. So the formula for acceleration is the rate of change in velocity. So this is the change in velocity over change over time, change of time. So acceleration is the final velocity minus initial velocity over final time minus initial time. For acceleration and deceleration, the formula is the same. So that's how we are going to calculate both of them. So let me call this one here acceleration 1 and here acceleration 2. So around this graph, I'm going to calculate this value. Acceleration 1, following the same same equation here, because this is actually is a slope, as you see, rise over the run. That's the same thing. So A1 here is the final, which is 20, minus 0, over the time, which is 30 minus 0. So now we have 20 divided by 30 is 0. Actually 6.7 meters per second square. And the deceleration, A2, is the final velocity here is 0. So this is 0 minus the initial one is 20 over the final time, which is 100, minus the initial time, which is 60. So acceleration 2 is minus 20 over 40, which is negative 0.5 meters per second square. So as you see, the acceleration 2 is negative because it's decelerating, and this one is positive. So the acceleration in magnitude is greater than the deceleration. Question 3. A lorry, which is kind of a small truck, like moving truck. A lorry is traveling along a straight horizontal road. A figure 1.1 is the distance time graph for the lorry. So it's in meter, and this is in seconds. The term I, the speed of the lorry while traveling at constant speed. The distance time graph that indicates a constant speed is a straight line with a slope. So in this case, we need to identify when the graph is not a straight line, when it starts to change direction. All that you need to do to determine up to when the lorry is traveling at constant speed, place your ruler on this line here and observe when it starts to turn. So right here is probably the last point where the line is still straight, right here. So let's mark this. So now let me find the correspondent on X direction, which is time, and the correspondent on the Y direction, which is distance. So the Y direction is intersect right on 2000 meter, but on the X is not. So I need to figure out how much is each box. So I have between 60 and 80. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 boxes. So I have 10 boxes between 60 and 80. 80 minus 60 is 20. So 20 meters between 80 and 60 corresponds to 10 boxes. So one box is 2 meters. So here we have 60, 62, 64, 66. So this number is 66. So the speed, the constant speed is the distance over time, and the distance is 2000 meters, and the time is 66 seconds, which is 30.3 meters per second, and we can round here to 30 meters per second. It should be fine. Describe the motion of the lorry into sections of time of your best choice. So we can divide this graph into 3 sections. Section A, the lorry is traveling at constant speed. As section B, the speed starts to decrease or decelerate because it's a curved line that is kind of with the shape. And then C, the lorry stopped. So right here, from this time to this time, the lorry is not moving. So it's moving at constant speed, is decelerating, and stop. From 0 to 66 seconds, approximately, lorry remains at constant speed of 30 meters per second. From 66 to 114 seconds, after that, the lorry is decelerating. From 114 to 140 seconds, lorry stops and remains at rest for the rest of the time. Because you decide the time for each section, another alternative, instead of breakdown like this, you could say from 0 to 60, 60 to 120, and from 120 to 140 for each section here, A, B, and C. Question 4. A student reveals some data about athletes and footballers. A. An athlete runs 12 kilometers in 1.5 hours. Calculate the athlete's average speed in meters per second. So here what we need to do is convert kilometer to meter and hour to seconds. So 12 kilometers and 1.5 hours. So what we are going to do first, let's take care of kilometer and do a multiplier here. So what you do is kilometer and kilometer at the bottom. And you do that because you want to cancel. So 1 kilometer you want to convert to meter. So what is the relationship between kilometer and meter? Is 1,000. So 1 kilometer we have 1,000 meter. Okay. Now next, then we are gonna cancel kilometer with meter, and we have meter as a result of the unit. Now let's take care of hour. So now hour is at the bottom, so we're gonna move to the top so you can cancel. So what is the relationship between hour and seconds? So 1 hour is 3,600 seconds. Okay, this way we can cancel hour with hour, and the units they are left here is meter per second. So now all that you need to do is 12 times 1,000 meter over 1.5 times 360 seconds. So what I did here is whatever was left after cancel everything, all the units, this is what we need to do our operation in the calculator. And this is what I have is 2.22 meters per second. Next question. Use the graph to calculate the distance traveled by the footballer during the 10 to 15 seconds. 10 to 15 seconds is right here. 10 to 15 seconds. So I have this area. Be careful, this is not a trapezoid, but there is a trapezoid here. We have a trapezoid on the top, and a rectangle at the bottom. We have two areas. So what I did here is, this is 6 meters per second. This is 3 meters per second. So the area of this trapezoid is big base, which is 15 minus 10, which is 5, plus small base, which is 12, 15 minus 12, which is 3, times the height, which is the difference between 6 and 3, which is 3, divided by 2. So this is 8 times 3 divided by 2 is 12. 12 meters. So at the bottom is easier, is base times height or length times width, whatever you decide. One side times the other one. So this is 15 minus 10 is 5, and this side is 3. So this is area 2 is 15 meters. So now we are going to add both areas, and area 1 plus area 2 is 27. So here is area, the total area is area 1 plus area 2, which is 12 meters plus 15 meters. And this is 27 meters. That's the distance corresponded to this section. Next question. Use this same graph to determine when the footballer is moving with greatest acceleration. Okay, there is 2 sections with acceleration here. If you're gonna call this section A, this section B, and this section C. Section A and section C, we have acceleration because the speed is increasing. But just by look, the type of which one is steeper, C is steeper than A. So C has a greater acceleration than A. One will be between 10 seconds and 15 seconds. So a good answer is that at section C, the graph has the steepest incline, hence meaning the speed increased faster than section A. Last question, question 5. A stone is thrown vertically upwards. The variation with time t of the displacement s of the stone is shown in the figure 2.1. Use this graph to describe, without calculation, the speed of the stone from t equals 0 to 3 seconds. Sometimes when they ask you just to describe, they replace with like a qualitative answer or information. Then you write just words to explain what's going on in the graph. If they ask quantitative, and then you have to use some calculation and some numerical values to describe or indicate different transitions in the graph. So this is a distance time graph and is a curved line, which means the velocity is changing, is not constant. So in this case, velocity is changing with a constant acceleration. You need to keep that in mind. Another way that we can do is draw a diagram to help us to define what's going on in this problem. Here it says the stone is thrown vertically upward. So let's pick up the story of the cliff. So let's say this stone is going to be thrown upward, and then is going to do this. So the stone is going to stop here. It's going to have about the same level here, same speed, and finally is going to hit the ground. So here is our reference line right here. This is our reference line where all start. So S here, or distance here, is 0. Even though is a certain height of the ground, so this is our zero point, where everything starts at 0. So as going up is going to decelerate, and right here is going to stop. So let's see how we can find the analogy in this graph. When you look at this graph right here on the top, on the symmetry of, I would say it will be right here, the symmetry, yes. So right here, momentaneously, this stone is going to stop because it's almost a flat line. A flat line on a distance time graph indicates the object is not moving. But this is just like a very small interval that stops. So let me cut this section right here in the middle. And this here, I will say that the stone is decelerating. So let me call this section, section A. Another clue that is decelerating is that any distance time curve line, we can pick like 1, 2, 3 points and draw a tangent line that is going to pass through that point but not cross the line like I'm doing right now. So as you see, that tangent line is getting flatter, is getting like less steeper. So that is an indication that is decelerating. Now what is happening on the other side up to here? So here the distance is 0. So looks like that's when it starts to come down. Now in this case is accelerating. And right here, go back to the 0 reference, which is on the top of that cliff. All right, so let's see what's going on, how we can determine by looking this curve, this is accelerating. Again, I'm going to select 3 points in this graph and draw a tangent line on that point. So here is like this, and this is like this, and this is like this. Now following the order over time, so the tangent line go like this, is getting less steeper, and here is getting steeper, as going down is getting steeper. So indication that on this side is accelerating. So now what is happening in this section? So in this section, continue to accelerate until, I don't know if the graph ends when the stone, it didn't say the stone hit the ground after 3 seconds, but if the stone hit the ground right here, this is the base of the cliff. We are using that as an example. Could be over a table, any other situation, but I'm using the cliff because I use this problem all the time to represent when a ball is thrown vertically. So then continuing acceleration here, that's what we see. So all these is a continual acceleration and is going down. You call this section, section B, from here up to where the distance is reference 0, and then from 0 to, from the top of the cliff to at the ground, for example, C. To determine the time between 2 and 1 second, we have 5, 10, 15, we have 20 boxes. So between 2 seconds and 1 second, let's say the difference here is 1 second, we have 20 boxes. So 1 box corresponds to 0.05 seconds. So here I have 1, 2, 3, 4, 5. So right here is 1.25 to 1.25 seconds. So section A, from 0 to 1.25 seconds, stone is decelerating. Okay, so between 3 and 2, here is the middle, this is 2.5. to 2.5 seconds. Stone is accelerating. Also add to section A, the stone stops at 1.25 seconds before change direction, before it starts to come down. So let's add this to the description. So at 1.25 seconds, the stone stops before change direction as going down. At 2.5 seconds, stone, let me take, I don't know where that stone. Stone reaches the cliff top height right here. That is the 0 reference. It doesn't mean, when you see 0 here, doesn't mean that stop, not like velocity. Is just that's going back to the reference point, but keep going. Didn't end here, the graph didn't end here. It says that end here, let's say someone throw a stone with a hand, and right here at the same height, catches the stone back, and then stop the motion right there. And that will be okay to stop right here, this graph. But the stone keeps going down, so which means that we have this portion right here, C, that is passing the reference point. So we can say here that stone is still accelerating. Is still accelerating from here to here. We still see like a curved line with a negative slope. We can also add that at time 3 seconds, the stone reaches the base of the cliff, right here. So this is like a negative distance. So this is the description of this graph, distance time graph, from 0 to 3 seconds.